Hi, welcome to this lecture on mathematical methods for biologists. In this lecture, we will discuss the topic understanding derivatives. Even if we don't know the equations to compute derivatives, can we still plot the derivatives as a graph? So this is a question that we will try and answer in this segment, in this part of the lecture. In the last lecture, we learned formulas to compute derivatives. For example, we learned if we have a function y, which is x power n, its derivative is n x power n minus 1. And we learned derivatives of many other functions, e power x and so on and so forth. We also briefly mentioned that if you have functions like sin x and cos x, its derivatives can be computed. Let me a little bit elaborate on this for a few minutes, and then we will come to the main topic. So, like we mentioned in the last lecture, if we have the function sin x, which is sin x, which can be written as x minus x cube divided by 6 minus x power plus x power 5 divided by actually 5 factorial. So, this is 3 factorial. So, this will be 5 factorial. So, a 6 I can write as 3 factorial. Let me write this as 3 factorial and minus x power 7 by 7 factorial and so on and so forth. So, this is the this for sin x, and the derivative of sin x, if you want to calculate, then we said in the like we said in the earlier class, we can find the derivative of each of these terms. So, x has a derivative 1 and x cube has a derivative 3x square. So, minus 3x square divided by 3 factorial plus 5x power 4 is the derivative of x power 5 divided by 5 factorial, where 5 factorial is a constant. So, I keep the 1 over 5 factorial as it is and find the derivative of x power 5 only. Then I will get this minus 7 x power 6 divided by 7 factorial plus dot dot dot. Now, this is 1 minus 3 divided by 3 factorial is 2 factorial. So, this is x square by 2 factorial plus this is x power 4 by 4 factorial. 5 divided by 5 factorial is 4 factorial minus x power 6 by 6 factorial plus dot 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 dot, and this will turn out to be just the cos x expansion. As you can see, cos x is 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial, which is 720 and so on and so forth. So, it turns out that derivative of cos x, sin x is cos x, so which you can directly do this and see. Similarly, we can also take this function cos x and find the derivative of each term. If you take the derivative of 1, you will get 0. So, if you find the derivative of x square, it will be 2x, and 2x will cancel with a minus sign, but here you have a plus x. So, derivative of cos x is minus sin x. So, if you do derivative of each term here, you will find that it is same as this series with a minus sign. Therefore, derivative of cos x is minus sin x and derivative of sin x is cos x. So, this is something that we can do from the equations that we have already learned. Now, the question is, if we know how to plot these functions, which we have learned plotting this function, because we discussed that equations are like graphs. So, if we plot this function, and by looking at this plot, by inspecting the plot, can we guess the derivatives without doing all these complicated calculations? Can we guess how the derivatives look like? So, let us learn that. That is the training that all of us should get. So, the training is to look at a function and guess and plot its derivative, at least how the derivatives would look like, how would they vary. This is something that we should be able to guess and plot. So, this is something that we will see. So, let us take this example of sine and cos. We know that derivative of sine is cos. So, let us now remind ourselves how does the curve look like. So, we all know that if we plot sin x, so let us plot sin x. So, if we plot sin x versus x, it would look like an oscillatory curve like this. There is starting from 0, then there is a peak and so on and so forth. Now, by looking at it, can we plot its derivative below here? So, the derivative of sin x, if I plot here, what will I get? So, let us train ourselves to look at this curve and plot its derivative below here. So, first let us look segment by segment. We said that derivative, we should take a small value of delta x and look at its derivative. So, if we take this small segment here, this small segment, if we consider this small segment, this segment has a derivative which is a slope, which is like a positive slope. So, we know that this segment has a positive slope. So, the derivative of this will be some positive number here. And if you look at here, this local segment here is almost like a flat line. So, it's almost like a flat line. So, we know that the derivative here, derivative of flat line like this will be 0. So, the derivative of this will be 0. So, the derivative of this segment is positive, derivative of this is the segment of this part where there is a maxima, it's almost like it will be 0 there. So, the derivative of this function is going from a positive number to 0. If you look at this segment corresponding to here, we know that this will have a negative slope. This is a negative slope. The slope locally here, if you look at the slope, this is a negative slope. It's a tilted function to this side. Therefore, this will be a negative value somewhere here. This segment, if you look at this part, this again has a 0 slope. Here there is a positive slope. If you look at this small segment, here, it will have a 0 slope again. Similarly, here also there will be a 0 slope. So, wherever there is a maxima or a minima, the derivative of it will be 0. This is something that we will learn a little bit more in detail, but if a function has a maxima, it is just changing from a positive slope to a negative slope, it has to go through a 0. So, therefore, this will be this point will have a slope 0. So, if I look at it, first I have a positive slope, then I have a 0 here, then I have a negative, then again 0 here, then I have a positive and then 0 and then again 0. So, the curve roughly, without knowing much about how the derivatives looks like, we by looking at zeros and positive and negative parts, we can guess that the curve would roughly look like this. So, this is going to be, if this is your f of x, this is going to be the df by dx. If I plot it a little bit more carefully, it would look like this. So, if I plot it more carefully, it would look like here. So, this is the precise plot. So, the red curve is sin x and the blue curve is cos x. So, as you see here, the derivative, the slope here is positive, therefore, cos x is positive there. So, at 0 the slope is positive near 0, therefore, the cos x value near 0 is positive, which is actually close to 1, and indeed it is 1 at 0. and this as the slope decreases, and here the slope is 0. Therefore, the cos function will hit 0 when sine has a maximum there. And here after pi by 2, this will have a negative slope. Therefore, the cos value will be negative. And as further here, the function will have another minima. So, another minimum. So, here in this minimum, again the derivative will be 0. Therefore, the cos x will hit 0, and so on and so forth. So, just by looking at small segments, whether the slope is positive or negative, one can guess and plot the derivatives of many functions. So, this is some exercise that before learning how to precisely compute the derivatives, we should try ourselves to guess the answer, what the answer would be. And this is an exercise that all of us should train ourselves, because when we do experiments or when we do simulations, we should have an educated guess on what the answer will be. Of course, the answers could have surprises, but if only we train ourselves to look and think about what the answer will be, what can we expect from our scientific knowledge so far, only then that will direct us, guide us in the right direction always. So, now we will think about some biological examples, some applications in biology. So, that is what we will do next. We will consider some examples relevant to biology and to understand and get some picture about derivatives. So, the first thing we will do is something which is everybody knows in biology, is the growth curve. So, if you consider a typical growth curve, and can we guess and plot its derivative by inspecting the curve without doing detailed calculations? We haven't yet learned how to calculate the derivatives of a curve given to us. If we get an experimental data, how to compute the derivative is something that we have not learned yet. We will learn this soon in the coming classes. But before doing it, can we guess and plot the derivative by inspecting the curve, by looking at it? So, this is something that we will do. So, first we will do an idealized growth curve. So, we all know how the growth curve looks like. Let me first plot a function. So, if you have an x-axis and y-axis, I will plot a function which not a growth curve, but it is somewhat related to growth curve, or if I draw a function like this, something which is small, then it increases, then it is a constant. So, this is not a growth curve, but it has roughly the shape of a growth curve, except that I have a sudden transition at some points. So, if I have a function like this, what would be the derivative of this function? So, if this is my f of x versus x, what would be its derivative? Can we inspect this and plot the derivative of this function? This is the question that we want to learn first. So, let us try doing this. So, let us first think about it. If we have this, the derivative of this part. So, here the function is flat. The function is not changing for many values of x. So, the derivative here will be 0. We know that the derivative here will be 0 because the function is not changing. It is a flat, the function is a constant. So, this derivative of this part has to be 0. This is like a straight line. So, this part will have a derivative which will have a constant slope. So, this is like y is equal to mx plus c. So, this will have a derivative m, which is same everywhere, like here or here or here. If you take a straight line, the slope here is same as the slope here, which is the same as the slope here. So, the slope of this curve is same everywhere. and here for this part, again the function is a constant, so the derivative of this will be 0 because the function is a constant, is not changing with respect to x. So, we expect 0, a constant, again 0. So, this is something that we would expect. So, let us redraw this as for our purpose. So, we have the function. So, let me draw this like that. I am just slightly redrawing it. You have this function which is small value increases and saturates. Now, if you, this is your f of x versus x. Now, what we want its derivative df by dx versus x. This is what we want to plot, and what we know is that up to this point the function is constant. Between this point, let me call this a, and this point b, between a and b it is like a straight line, and then beyond that the function is 0. So, here up to the function is up to c, and up to this the function is 0. So, this is the function how it would look like. So, now if we plot the derivative for this, here the derivative is 0. So, I would draw the derivative here as 0. So, I am drawing at 0. Here there is a constant value. So, let us that constant, some positive constant. So, let me draw some positive constant. So, it is this is the positive constant. So, from here to here the derivative is same, it is a constant. If it is 3, it is 3 everywhere. If it is 4, it is 4 everywhere. Whatever be the value, some positive value. And here onwards again 0. So, again 0. So, it is almost like a step function if you wish. Suddenly it changes. So, the derivative would look like this. Suddenly the derivative changes at this point. It is almost like discontinuous. Sudden change, which is typically does not happen in nature, but even though there is a sudden change and then again suddenly falling, and then we have this. So, this, if we are given this f of x, the derivative is df by dx, which can be plotted like this. Now that we did, it is easier for us to think about a growth curve, because growth curve is a smooth version of this. So, if we smoothen this curve, what would be the derivative? How will it look like? Try this yourself, but we will quickly look at it. If we quickly see this growth curve, the typical growth curve would look like this. So, this is a smooth transition now. And if we want to plot its derivative, so this is our f and f of x, and now we want df by dx to be plotted. So, we know that roughly up to here there is almost somewhere here, even though I cannot precisely tell the point, somewhere here there is a transition somewhere here roughly. So, but the transition is very smooth. Therefore, if I plot, the derivative early will be 0, but it will slowly pick up, and here it will be maximum. So, somewhere here you will have maximum derivative because it is a smooth function, it is not like a straight line, and again it will hit 0 here. So, it has to reduce and come down nicely to 0, and then it will stay closer to 0, slowly it will reach 0. So, something like this. I did not plot very nicely, but it is a smoother version of a function that we drew, which is, it has to be more symmetric. Maybe there is a slight asymmetry in what I plotted, but nonetheless the idea is what I described. So, please draw yourself, look at it, and then train yourself to plot the rough derivatives. If you have this, the derivative will roughly look like this. The precisely how will it look like, that we will learn how to precisely understand, plot derivative of a function given to us. But before doing it, we know by inspecting different parts, for this part it has to be 0, for this part it has to be positive, increasing. So note here, it is slowly increasing from 0 to a positive number. Therefore, it is slowly increasing from here. Similarly, slowly decreasing. So here the slope is slowly decreasing. So here also is slowly decreasing. Somewhat like here also this curve will come down. So this is the idea. Now let us go to the next example. So the next example is microtubules growth and shrinkage. So many of you who has studied biology has heard of this polymer called microtubule, which is a polymer, is a cytoskeletal filament in our cells. This has a property, at least in vitro experiments, when you look at microtubules, what one would see is that microtubule would grow and shrink rapidly. So they polymerize and depolymerize. So experiments have shown us how the length versus time data for microtubule would look like. So if I plot the length versus time data for microtubule, typically it would look like the following. So let me plot here length versus time data for microtubule. So microtubule is a polymer, of course. So it has start with a small length and it grows slowly up to a point, then suddenly it shrinks, almost rapidly it shrinks. Then it grows slowly, then pretty rapidly it shrinks, then grows slowly and shrinks rapidly. So this is how typical length versus time curve for a microtubule would look like. So these points are called catastrophic shrinkage. So this point is called a catastrophe, where sudden shrinkage happens and after some point it grows again, and this is sometimes called rescue. So this is the typical, doesn't matter the details, even if you don't know the phenomenology of microtubule, just understand that microtubule is a polymer. Microtubule is a polymer. Microtubule. Its length increases with time. It polymerizes. Suddenly it starts depolymerizing and shrink. Then it again polymerizes. Sudden depolymerization. Polymerizes. Depolymerizes. So when I say sudden depolymerization or a slow shrink, slow growth and sudden depolymerization, what do I mean? When I say slow growth, I mean, what I am trying to say is that the length increases with time slowly. That means it takes a long time for it to polymerize. Compared to this, the shrinkage is very fast. So if you look at the time here, this would be, if you take in minutes, this could be in some many hundreds of seconds, for example. It could be some minutes, and this is time, and here there is shrinkage. So if you look at this length versus time, what we would see is that there is a slow growth, so this takes a long time to reach, and there is a sudden shrinkage. This is shorter and this is long, this is short, long, short. Now if you look at this and plot its derivatives, so here we could plot its derivative. So what I am going to plot? I am going to plot dl by dt versus t. That is what I am going to plot. So plot dl by dt versus t. So here there is a positive slope, which is a small positive number, because the slope is not very big, some positive number. So, I will draw a positive number. This is like a straight line. This is like a straight line. So, I have a same slope up to this point. So, I will just extend this. So, let us extend these points down. So, what do we have? Up to this point we have a straight line. So, we have a constant slope, which is the slope of a straight line, which is this. And there is a sudden shrinkage. Sudden would mean large negative number. This is what sudden shrinkage would mean. The slope is large compared to this. It's like larger, and shrinkage would mean it's a negative slope. So, then it's a small negative number. It's a big negative number. Compared to this is much bigger. Then it is a constant. It's almost like a straight line. Then suddenly it's a positive again. So, it's a large negative, small negative number. It's like this, and then again this. So, this is how the dl by dt would look like. So, slow would mean that this part, this number is small, which would mean slow. This is much larger, this is much larger, therefore it's a fast shrinkage. So, the training that we want to give you is basically to studies, to tell you to think about a given data or a given phenomena. Let it be biological or any phenomena that we see around us. We saw two examples, a growth curve and a microtubule. Given this phenomena, how will we draw the derivative? So, what is the meaning of the derivative? That is two things that we will learn. So, here think about what is the meaning of dl by dt. It's like the rate of shrinkage, and we will come to that in detail and try to understand. So, we want to summarize what we learned now in this. So, we learned essentially one thing: look at graph, look at the plot, look at the graph and plot derivatives. This is the thing that we learned. How to plot derivatives just by inspecting any graph given to you. And in the coming lectures, we will learn how to precisely calculate this, how to quantitatively calculate this given a data set. So, with this, I will stop today's lecture. Thank you.